Greetings and welcome, ladies and gentlemen. Welcome back from the summer. Welcome to the start of Mathematics 4. That's right, Math 4 coming at you. And today we're in our very first chapter. We're talking about systems of equations. We're going to talk about many ways of solving systems. And today specifically we're referring to solving systems by substitution. Now, we started off today's class looking at a 2007 kneecap question, which we, after defining some variables, that's how I'd say it, and writing some equations, we talked about how could we solve these two equations and two unknowns. And we had a student offer up a possible solution and ended up coming up with an exact solution. And the method that the student used was, in fact, substitution. So before we get any further, I actually want to tell a little story, and I'm going to draw some pictures. Normally I'd act this out, but I can't get my webcam to work. So here's a little dude. You don't have to draw this picture. And in fact, this is not just any little dude. This is Indiana Jones. Okay, there's Indiana Jones, right? So perhaps you know of this, the very first Indiana Jones movie, right? Where he goes into this cave at the beginning of the movie, and there's all sorts of traps, and there's spikes, and there's pits that he has to go through, and all sorts of stuff, right? And he goes through all of this, and then eventually there's giant boulder that will chase him out of said cave, right? And he even has there's also the classic little moving wall. That no, and then maybe he'll reach out and grab his hat last minute. That kind of looks more less like an Indiana Jones hat and more like a man in the yellow hat. And I think I'm gonna just roll with that right there. There's the man in the yellow hat, and we'll pretend that Indiana Jones and the man in the yellow hat are the same. So at the end of this scene, right, he ends up coming to this little pillar. Right, and there's on this pillar there's this little golden idol. I don't know if you know what I'm talking about. All right, and it's this little golden idol, right, like that, right, and he gets over to this golden idol after kind of chessboarding his way across the room carefully so as not to hit one of the little traps that was kind of like one of these things and it had a hole in it. And then, oh no, Indy, look out, don't step on that, because suddenly, spear, that's a terrible, dull spear, nonetheless painful. There we go. And it would shoot out of the floor. So he knew how to dodge that. And he finally gets over to this little golden idol. And as he's standing there, and his hand's about to grab it, here's a hand, and he's about to grab it, right? He's like, wait a minute. He's like, and is kind of pondering his situation. He says, if there were spikes and walls and pits and soon-to-be boulders and these spike floor tiles, maybe this little thing is trapped as well. And he comes up with a solution. I don't know if you guys remember this. And no, it wasn't a rock. He actually, earlier, before he even got in the cave, he planned this, maybe he'd studied, he actually took this little bag, right, and it was full of, this is sand, right? It was a bag of sand, and he kind of estimated the molecular weight of gold and calculated how many moles of gold were in this statue, and also knew the molecular weight of sand and perhaps what elements were in it, because he's a professor, after all. And he ended up, taking these two things, right? So here he is, he's kind of holding this in his hand now. That's kind of, I don't know how that's a hand, but we'll pretend. And so he's holding this in his hand, and he kind of weighs it and estimates the weight of the statue. And what he ends up doing, ready? He does one of these. What does he do? He plans on this being, oh, no, that was an ugly arrow. There we go. This is his goal, is some sort of switcheroo is his goal, right? Let's see, bam. Look, I even filled in those arrows. Super important. I'm going to actually add some nice little shine to it as well. So he ends up doing this little switcheroo, and the theory behind the practice is accurate, right? This is the substitution property, right? His thought was if this is truly equal, right, to that, if that, man, there we go. All right, that's a good equal sign. If those two things are equal, then they should be able to be interchanged at any point because they're equal. And he assumed that this little pillar trap that was here perhaps only measured the weight of whatever was placed on it. So that's why he was going to use this concept. And if you don't know, I don't know, it's an old enough movie. I can spoil it, right? So he ends up placing the bag of sand on it and getting the golden idol, and then the pillar starts moving down, and he's like, uh-oh, and then like rumbles all throughout the cavern, and he starts running, and then he's all like, no, and he runs away from said boulder, right, and then he runs, right, and the boulder chases him, and his little buddy betrayed him, and it was sad. But he gets out of there, and then I think at the end he ends up, there's another dude that takes the golden idol away from him because he had a tribe of dudes with him. But anyways, my point is substitution is what's going on. Substitution. And the idea is if two things are equal, they can be exchanged at any time. And that's actually what we saw take place in this little step right here. Right? Our student solved one of the equations for one of their variables. This little expression here was equal to x. And if this is equal to x there, that means it's equal to x all the time. So she substituted this expression in for x, and you can see the same expression right there and right there. So she like kind of, now notice Indiana Jones, first of all. He didn't just like throw sand on this little pedestal. Like he wasn't like some sort of caveman with sand. Like he put it in a nice little bag, right? Otherwise the sand would have just like fallen all over the place, and that wouldn't have been cool. So notice she did the same thing. I don't know if you caught that right here. Look at this. These parentheses, are these not behaving like a bag, a holding little container that kind of held it in place? So like her math doesn't just fall all over the place. That's exactly what she did. She put it in a nice little baggie. And then that way she remembered to use the distributive property and solve from there. And then once she solved for one of them, she was able to plug it in back into what's called the revised equation and solve for the second variable as well. And as long as you have proper labels, right, you know that, y equals 5. What does 5 mean? 5 is, the number of deluxe violins in this problem. And then that would allow you to answer the question and have properly shown your work. So that's the idea behind substitution. Find two things that are equal and interchange them is the goal, just like our friend Indiana Jones would do. So what I'm going to do for us is I'm just going to lay out some steps. Solving by substitution. Substitution. And here we go. Step 1 is solve. Now, because in our situation, we've got multiple equations and multiple variables. So step 1 will be solve one of the equations for one of its variables. And now my English is going to demonstrate failure. What's the thought? Apostrophize this it's. Possessive? Which one's possessive? Hey, you got me. One of its possessives variables, right? So whichever one you want, I guess. Does the apostrophe have the it is in that case? I always mix it. Right. Okay. Well, anyways, there's step 1. And that's what our student ended up doing here, right? We had x plus y equals 20, so what did she do? She isolated one of the variables. She got x by itself by subtracting y from both sides. Step 1 is done. Step 2. All right, by the way, step 1 is called the revised equation if you want to give it a name. And that's not just a name I made up. It's, I would say internationally known, but we have a student here that's international, so you'd probably call me on my lie. Even though mathematics is an international language, I suppose some of the nomenclature may differ at times. So let's see, revised equation would be that. And now step 2 is substitute the expression in for the variable in the other, really important right there, other, underline there, equation. In fact, you'll get some false positives if you plug it back into the equation we'd originally solved, where later on, when we gain some ability to analyze the types of solutions we have, you'll get a false positive telling you that you have infinitely many solutions when that may not be the case. So beware. And then step 3 is solve that equation or whatever. Solve the equation. Because even though it might be an ugly equation, it will only have a single variable, and that'll be great. And then step 4, I'll just say substitute again your answer into the revised equation. There, and solve, right? And then you'll have both of your solutions, if in fact we happen to have a 2-variable system, okay? So I'll let you finish writing that. Right, but the general principle behind this is exactly what old Indiana Jones was trying to do, right? If I find 2 things that are equal, I can interchange them at any time. So, so notice, right, once we'd solved for one of the variables, we said, oh, y is equal to 5. That means I can take 5 and plug it in for y at any point. Now, technically, at this position, you could have plugged it in here, you could have plugged it in here, or you could have plugged it in here. The best place to plug it in, though, is the revised equation, because notice, the revised equation is already solved for the variable I'm looking for, right? If I plug it in here, I wouldn't be wrong to plug it in either of those. I'm just creating additional work for myself. So that's all. So that's why you plug it into the revised equation there. And that's how we solve by substitution. So let's actually do a substitution problem using kind of these steps. I'm going to scroll over to the right column here. And let's see, let's do an example. Solve using subs. There we go. And let's solve this equation here. 2x plus 3y equals 8. And let's have x minus y equals dos. So here's a system. Sometimes systems will be denoted with like a curly brace there. Bracket. Braces. Is braces plural and bracket singular? That sounds probably right-ish. Nonetheless, this is a system. Basically, it's saying, all right, you've got 2 unknowns, but you also have 2 hints to help you find those unknowns. If I had 2 unknowns and only 1 hint, I couldn't solve this riddle, right? And essentially what I'm looking for is, right, this equation has, well, first of all, there are infinitely many combinations of x and y. This equation restricts some of them to a line. That actually represents a line. And there are infinitely many points on that line. There are also infinitely many points on this line. And I am looking for the one point, the holy grail of all points that Indiana Jones would be searching for, that happens to exist on both of those lines simultaneously. All right, so that's my goal. And you actually could solve by graphing. You'll find some videos online about solving by graphing, I'm sure. I'm not a fan of graphing, however, because graphing often is not very accurate. It's got some weaknesses. So let's actually keep going here. So step 1 in substitution. What was step 1, guys? What should I do for step 1? Okay, solve one of the equations for one of its variables. So I've got 4 possibilities. I could solve for the first equation's x. I could solve for the first equation's y. I could solve for the second equation's x. I could solve for the second equation's y. Which one would you want to solve for, and do you have any reasoning for it? Anybody? Why do you like the second equation's x?
There's no coefficient.
Wow, perfect. Language as well, right? Now, if I solve for this first equation's x, right, I would have, probably subtracted 3y from both sides. And how would you get rid of the 2 in front of the x to get x by itself? You'd have to divide, and what does dividing create? Fractions, which are fine. They're fine. They're okay. I love fractions. In fact, I might even say I'm a fractionophile. But I know most people aren't. In fact, some people hate fractions unjustly. But they're just like every other number, and it's about time we had equality in the way we treat numbers. But nonetheless, this would create fractions, and you could actually still work through the whole problem and still substitute. But we might as well play it smart, right? So since this has no coefficient, I'm not, even if I did have to divide by the invisible 1 here, I don't have to worry about that. It's not going to create fractions. Somewhat equally good variable would have been the second equation's y, because it has a -1 coefficient. I would have to change the signs at some point, but I would say targeting this would be preferable. So let's do that. Let's solve for the first equation's x. So how would I get x by itself? Or sorry, the second equation is x. How would I get that x by itself? Add y to both sides. Good. So I'll have x equals y plus 2. You could write 2 plus y. There's no problem with that. So this is my revised equation, recall? Right? Remember? So that's the RE. And now what do I do? So I'm going to, since these two things are truly equal, right? Bag of sand, golden idol. I'm going to interchange this where? Does it matter? Oh, in for x. You're right. Okay, so it is going to be in for x, and it does have to be in the first problem. If I plug it into the equation I just solved, that's when I'll get that false positive saying that I have infinitely many solutions. I'll end up getting 2 equals 2, and that is a true statement, but hopefully not new information to us. So let's see. So let's plug that in, and I'm not just going to write 2 times y plus 2 like this, right? That would be very bad, right? Indiana Jones wouldn't do that. What would Indiana Jones do? Yeah, put that in a nice little pouch, a satchel, a bag or something, right? Put some parentheses around it, suggesting that this whole, right, 2 times x, the whole x is being multiplied by 2, so this whole thing must be multiplied by 2, all right? And now I can solve this equation. This is perfect, right? So 2 times y is 2y plus 4 plus 3y equals 8. And I can combine some like terms perhaps. I have 2 y's and 3 y's. So how many y's do I have? Right, 5y plus 4. Good solving skills. We got to practice coming back from the summer. I don't know, maybe you guys were solving equations all summer long. That's a possibility, I suppose, some of us. Oh, but yeah, actually, I know some of us were. It's true. So I have 5y equals 4. All right, now what do I do? Divide by 5. That's a really ugly looking 5 there, but that's okay. Divide by 5, and I get y equals 4/5. Now in our violin problem earlier, we didn't allow fraction answers because you couldn't buy a fractional portion of a violin. So this is not necessarily wrong, it's just a fraction. So that's fine. Now what would I do? Am I done? I've boxed an answer. I must be done, surely. No, I'm not done. What do I have to do? Yeah, and where should I do that? You could actually plug it into either of the original equations, but the best place to plug it in is the revised equation, because this will always already have been solved for the other variable that I'm looking for. So out of a matter of convenience and efficiency, we'll plug it in right there. So I'll get x equals 4/5. Technically, you could throw some parentheses around it in case, well, if that was like a 2y or a 7y or something, you'd want parentheses around it. It doesn't actually matter in this case. plus 2. Oh, boy. Man, adding fractions already. But that's okay. 4/5 plus 2, what's that? 6/5? What do I do? How do I do that? Okay. What's the common denominator here? And actually, these LCD skills will come in handy tomorrow in our next video. Multiply by 5/5, which really, what is 5/5 equal to? 1, and I'm allowed to multiply something by 1. It's not going to change it, right? So that's allowed. That's not changing its value. It's just going to change the way it looks. So I'll have x equals 4/5 plus 10/5. And how many fifths is that? 14/5. And I'm actually a fan of that answer, unless I had to bring that into the context of, like, if x was a number of miles, I wouldn't say that I traveled 14/5 miles. That wouldn't be very helpful. And in that case, you could convert it to a mixed fraction, which I believe would have been the 2 and the 4/5 in that case. But I'm a fan of improper fractions as well. So anyways, that's a general outline. I know I only got, well, I guess I have 1.5 examples on this video. But I think it's good enough for now. It had a lot of explanation. I'm happy with it. So goodbye, Internet friends. Bye-bye.